Hello chaps and chapettes. Today we're going to be continuing on with our look at voltage. And instead of the EMF part, we're now going to look at what's called potential difference. And that's going to be subtly different. By the end of this video, what you're going to know is that potential difference is the difference in voltage across a circuit and also individual components. You're going to understand that potential difference is completely used up across all the components in a circuit, as in it starts at a high bit and then ends up at effectively zero. And you should be able to use a voltmeter correctly, as in hook it up to a circuit in the correct way. It is different from the ammeter well we've done before, so make sure you pay attention. So, first thing you need to do. First of all, you need to be able to say that potential difference is the difference in voltage across a circuit. And that's kind of easy enough to say, but it's difficult to actually know what it's talking about there. What it's talking about is the difference in energy levels as you move through a circuit. And you can imagine that as being our electron, which carries a certain amount of energy, as we talked about in the last video. And as it goes through the circuit, it loses a little bit of energy each time to a different component, or to different components. Some components will use a little bit more energy than others, so that's effectively more potential difference dropped across there. And by the time your little electron gets to the end of the circuit, it's given away all of its energy and it's ready to pick up some new energy at the cell. So there's a couple of ways we can look at that. And before we go to the back of the classroom to show you what I mean, make sure that you hit the like button so that the YouTube algorithm knows I'm here and that these videos can be shared out to a wider audience. Thank you very much. I do appreciate it. So let's go to the back of the classroom. Right. This is actually the second time I'm doing this. Hopefully I get it right this time. So first of all, we're going to do a very simple circuit, okay? Just going into a light bulb, so cell and a light bulb. And I'm just going to redraw this one so that it kind of makes the analogy better. So we're going to start off with the cell up there, and then we go to the light bulb there, and then just going to loop it back around, okay? The reason I'm doing it this way around is just so we have a nice long line of stuff. Let's move that a bit closer there. There we go. So, first of all, we are going to need our electron. And that's going to be over here for now. And it's going to be in a low energy state, okay? And what's going to happen is our light bulb is going to encounter the cell there. And what the cell is going to do is it's going to provide it with some energy. And that's going to be represented by our electron going up an escalator. So now it has some height energy, okay? Let's move that a bit closer there. Now as our electron continues on its path, it's then going to encounter a light bulb. And what it does is it loses its energy down like that, okay? And that means that as it goes past the light bulb, all of that height energy is now lost, okay? And that's the idea of potential difference. When we leave our cell, we have a higher potential difference, and as we go across the components, we lose it, okay? And we go back to our original height. Now there is a difference in the height there, okay? And we've just talked about this in terms of height, so that's going to be like gravitational potential energy. So we have a change in potential, or a difference in potential, or a potential difference. Now this is just an analogy. Doesn't mean that the electrons are like jumping up and down inside the circuit, although they kind of are. What this means is that they're going to a higher energy state through a cell, and then they drop to a lower energy state in the light bulbs, which means that the energy here is now transferred to the energy over here. That's what makes these things really, really good. Now, if we start adding more components on there, hang on, bear with me while I just redraw this one. There we go. If we add, okay, so now if we add more components on there, what will happen is the electron drops down a little bit, and then drops down some more, so that the potential difference is shared across all of them. So there's going to be a small change there and another change there. So if we just give this like, well, I don't know, Vt, okay? This is going to be V1, V2. So what we have then is the idea that Vt is going to equal V1 plus V2, always. And what will happen is the electron is going to share its energy across all the components. And the way it shares its energy is going to be dependent on the resistance of each individual component. If this light bulb has higher resistance, then this is going to drop more voltage across this one than it would this one. Basically, how much energy does it take to kind of like push through the light bulb? And well, that's the idea. So what you should take away from this one is that the voltage goes up and then drops down as we go through each component. And this is basically how you can work out how much terminal voltage is across each of your cells if you only know the voltages across there. At least in a series circuit. Parallel ones get a bit more tricky, but we will discuss that later on. Right, so a couple of things I just need to make sure you understand in that one. The voltage must be at its maximum at one end, and it should be 0 at the other end. So essentially at the front part of our circuit, so the positive part of our cell, you should have high voltage, and at the end you should have 0, okay? As in all the energy should be used up by all the components in that circuit. Now there are some very clever circuits which you might come to see if you do computer science or A-level electronics, but as far as GCSE physics is concerned, you start off with a high number and you get to 0. What that means is if you start adding up all the voltages dropped across your components and you end up with a number that isn't 0, as in, you still have some voltage left over, something has gone wrong. Go and check your answer, or just make sure you've actually put down the correct values for your circuit. And well, that's as much as you need to know about the theory of it. What I'm going to do now is show you how to actually measure voltage. It is subtly different from using an ammeter. And well, let's just jump straight into looking at a voltmeter. Now I did look for an analog voltmeter. I don't actually have any, probably because I don't think anyone really ever uses them. All I've got is my digital multimeter here, which I hope has got enough battery on it. So just to show you the circuit first of this one, so you know how we're doing this. This is a typical circuit. So light bulb, I think I've drawn it like 5, 6, 7 times today actually. What we're trying to do is work out the change in voltage across components. So we need to put our voltmeters around the components that we want to measure. The idea here is that we want to see the difference in voltage from here to here, okay? And well, there we go. So if our electron is carrying like 2 volts on this side, and it must therefore be 0 volts on this side, then it's going to use 2 volts from here. So it starts off 2 volts there, ends up 0 volts there. We want to find the difference, and that's what our voltmeter is going to do for us, okay? So obviously if we know the voltage coming out of this thing, we don't have to use these ones. But, okay, we're not going to have like the electron telling us what voltage it has. We have to go investigate that. So this is definitely not how you hook up a voltmeter. This is taken from the ammeter setup from before. So what we're going to do is just switch this to voltmeter mode. There we go. And I'm going to plug this into the voltmeter sockets. So quite easy. We've got a V there for voltage, and we've got the COM there for common. So there we go. Again, this is not how we hook this up though, and actually I'm going to need another wire. Here we go. So we need to hook this up in parallel. Easiest way to do this with any circuit is to in fact hook up the light bulb first. So let's just hook up the light bulb first. There we go. So before you add your voltmeter, just make sure you set up your circuit first. So I've got a power pack here. And there we go. Oh, these dodgy wirings. There we go. There. There. All right, so we've got the light bulb now working. So the second thing we do, put the sockets in our voltmeter, and then all we have to do is place our voltmeter around the components we want to measure. So that's going to be nice and easy. There we go. So we've got this plugged in on one side and the other side of the component we want to measure, which is the light bulb. And that's reading a voltage of 7.27. Now some of you might notice that I've got an annoying minus number there. Don't panic. We just swap these terminals around and there we go. Nice positive numbers. So we don't have to mess around with that negative number on the malarkey. Now, okay, some eagle-eyed people may notice something strange about this one. If I show you this, you can see that's showing 8 volts on the power supply, which is not, well actually no wait, that's the wrong one. We're looking at the DC one, which is the outside track, so that's actually 10 volts on the power supply, which is not what we've got here, okay? And that's going to be the difference between the EMF supplied by the power pack and the terminal voltage we got out going into our light bulb. Basically, what we're saying is in this one, you can never trust the dial on the power pack or the number on your cells or batteries. You always have to measure your voltage because those things don't give you the right answer. Always measure voltage and then you'll get a good answer. So, there you go. Right, so I hope that was helpful to you. The challenge today is to discuss this. Which is going to be more dangerous? High voltage or high current? Now, I know what you're going to be thinking. If you've got high voltage, you should kind of have high current. Probably true, not always true. Sometimes you can have high current with a low voltage and sometimes a ridiculously high voltage and a teeny tiny current. And in fact, we will look at that later on. We look at transformers and the national grid. But which is more dangerous? High voltage or high amount of current? You tell me in the comment section below. I'm looking for the reasoning on here, just not which one is which. So there we go. Other things that you should know from the end of this video, you should know that potential difference is the difference in voltage across the circuit as you go through different components. You should understand that it's completely used up across all the components in a circuit, and you should now be able to draw and use a voltmeter correctly in your circuits. And there we go. Right guys, I've actually got a little bit of new equipment here. This is my new microphone. Oh, I shouldn't have touched it there. Let me know if the sound quality is any improved. And I'll catch you in the next video. See you later, guys.